This video is sponsored by PCBWay. So if you're curious how this label maker works, or how two stepper motors can write letters and numbers, or how does this machine even know what the letter A and number 4 look like, well, I'm glad you're here because I took dozens of minutes to figure it out and write it up. We've got code, we've got a quick unboxing, build montage, and even have my kid wondering the same thing you're wondering. How does this change digital letters into an analog drawing? Really though, I got this in the mail after finishing the Domino Robot Mod video, and I tore right into it. This robot, I'd say, is more neat than fun. It's a label maker. How much fun can you have making labels? It's not like I have OCD. What I did like about this is that I've never actually used stepper motors in any of my projects. So how does this change those letters into drawings? I want to start with my 4-year-old son asking the same questions you have.
But does that spell printing?
Yeah, it spells printing because that's what it's doing.
I want it to spell train.
It is up here. See, T-R-A-I, and it's going to do an N. Okay, so he's probably a little more confused than you are. Hopefully you're aware it's not writing the word printing, unless that's what you wanted. But I've been able to put this to a more practical use. The larger letters have actually been nice, so I don't have to hunch over so far to see what I labeled my drawers are, and labeled some bins with USB cables and whatnot. All right, so let's get started by looking at what makes this thing tick. Before that, I want to introduce you to PCBWay. They can take your idea and help you with custom PCBs, 3D printing, and CNC machining. They even have videos to help you get started. I've seen them used in many projects across the web and hope you check them out with the link in the description below. If you use them, please let me know in the comments. Okay, so we're going to cover the code from start to finish in a minute. But first, I want to print more characters on the tape before a full revolution, and I want to do some smiley emojis. If you've modified Hackpack code before, you'll know that there are 3 different levels. Level 1 being stock code, level 2 being variable updates, which oddly enough will allow us to change the scale, but not other characters in the alphabet. So we're moving to level 3, which allows you to edit everything. When scaling or offsetting variables, I personally like to do the math right as we define it, so I can retain the default or original value. So by multiplying by 75%, we're shrinking the width of each character by 25%, because 1 minus 0.75 is 0.25, or 25%. Then we'll add our semicolon and parentheses to our alphabet array. When we step through the code next, we'll see that these are already defined, but unused. Build, upload, let's test. While it takes a minute to scroll for our smiley face, it does indeed work. Next, we'll type out Arduino and Raspberry Pi, which, without our 25% reduction in width, would overflow and start writing over itself as the pen came full circle. After finishing it, looks like we finished with room to spare. I like these larger labels because I can see them from farther away, so maybe I'll update my labels later with a black pen and some white masking tape. Okay, now that we've made basic changes, let's step through the stock code to see how this thing actually works. First thing I notice is that we have some new libraries we're including, like the LCD, stepper motors, and the joystick. Scrolling down, we have expected variables like scale, available characters, and some enumerators for application states. As usual, there are tons of comments, so we're going to move on to the meat of the label maker. This gigantic 2D array is essentially a mini algorithm represented by unsigned 8-bit integers. This defines characters for the stepper motors to move to. It says here that the X value is represented by the 1's place and Y is represented by the 10's place, meaning that we have a 10 by 10 grid to make a character out of. The 100's place has a 0 or 1 representing a boolean to enable the drawing of this step, and a 200 represents stop drawing this character. It also looks like a 222 can represent a dot like a period, question mark, or an exclamation mark. Setup just has some initialization and homing, so we're going to skip it for this video. Our loop starts by getting the button state, whether it's pressed or not pressed, and what the direction of the joystick is, if it's even being used at all. Once we store that data in variables, we move to a switch statement based on the current application state. The main menu state has an if block if we're moving to the main menu state. To clear the LCD, print the start word and update the previous state to main menu, which is the current state. Then every half second we'll blink a greater than symbol next to the start, and if the joystick is clicked like a button, we'll move to the editing state. The editing state will clear the LCD on transition and once again update the previous state to our current editing state. Next, in every loop, we'll print the semicolon and the current text we have so far, meaning every loop we refresh the display. This is important to remember when it comes to changing letters. Remember that current character is an int for the current index of the alphabet array, so when we go up or down, we increase or decrease this value by 1. After modifying the current displayed character, we'll print our update to the LCD and wait a quarter second, since a loop without delays executes as fast as possible. If we're not scrolling, then flash the current character every half second. The next if statement checks for left and right movement. If left, then trim off the last character of our entered text and refresh the display. If right, then add the current character selected to our text string and let the loop handle the refresh. Finally, if the joystick is pressed, add the current character to our text and change the state to print confirmation. Print confirmation will display the yes and no values and move the blinking greater than sign left or right. When you click the joystick, you're either moved back to editing or forward to printing, based on whether the cursor in position 2 for yes or 10 for no. Finally, the printing state updates the LCD to display printing, then calls the plot text method, which does almost all the heavy lifting for us. After the printing is done, we'll return here, move to a new line, clear the text, and reset our state back to editing. The plot text method takes in our current text string and the current X and Y position, which is 0 at the moment. For each character in our string, move over if it's a space, or call plot character. Once we return back here, then move our X position based on the current character we're printing and our scale variable, defined early on. When I changed my scale to 75%, it updated the math here to shrink the horizontal space used. The plot character method starts some actual work. First, a uint8 is an 8-bit unsigned integer, also called a byte, so it'll always be positive. What it looks like we're doing here is making character-specific changes. We look at the passed in character C and create a character variable from it, which will be used as the first index when looking up our 2D vector array. It looks like the alphanumeric characters get an offset while others get a hard definition. When we loop through each vector defined for a character, remember the second length of our 2D vector array is 14 units long. If the next vector is a 200, then return, otherwise check if our hundredths place is a 1 or 0 and store it in the draw variable. After some scaling to compensate for the motors, we'll call the line method now that we're fully prepared to draw. The line method starts to move our stepper motors. If drawing is 0 or 1, then call the plot method, which will either raise the pen or lower it onto the tape. Once the pen is placed, then figure out the delta between where we are and where we want to be. Breesenham's line algorithm only works in positive coordinate quadrant. This algorithm is a good read if you're wondering how pixels are selected to use when drawing a line. Sounds like they had some issues getting it to work, and the solution was to differentiate the logic depending on whether the x delta or the y delta was greater. Ultimately, for every distance in x or y we need to make, loop that many times asking the stepper motors to make a step. Finally, store our new end positions. Like the previous two hack packs, we have ourselves a small black box with a manual on top of all parts in a plastic bag or anti-static bag. Contents include a joystick, LCD screen, stepper motor drivers, Arduino Nano, servo, markers, the stepper motors themselves, a bag of bits and bobs, breadboard, battery, wires, a new gear, tape, some thingamajigs, and finally our wood support. So we're going to start by adding quite a few standoffs to this LCD. I had some issues with these since they are so small, but my little sausage fingers managed to get the job done. Once we have the LCD screwed into its position on the wood plate, we're adding a few more standoffs to the joystick and also screwing that in. Moving on to the stepper motor drivers, we're adding, again, even more standoffs, and again, screwing those PCBs onto the wood plates, and we get to do this twice. Next, we screw in a stepper motor onto the wooden arm, which will eventually be used to rotate the tape roll. It'll be easy to orient it in the right position because the wood is cut so it only fits one way. When we screw it onto the baseboard with a big old washer, and make sure to test its rotation with a few Pac-Man type chomps. The next part is the assembly to move the pen up, down, in and out. We already have our gear and pen holder in place, and now we get to attach the second stepper motor. Again, it screws into place, and the screw holes are offset, so it only attaches in one orientation. The servo should be oriented a specific way, with the wire going away or up from the pen holder. This is because the servo cares about its angle to move the whole sled in and out against the tape. Finally, we need to install the guide rods and pay special attention to the orientation in the book, because I didn't and had to fix it later since it was backwards. The guides are keyed with a triangle, so set it in place and screw it in. The spool for the tape gets another washer and a long screw. Once it's in place, secure it with a nut underneath and give it a spin. Flip it over, attach the badge holder, and place the end in the notch on the sled. This was when I realized mine was backwards since I had no place to put this thing, and it got it fixed quickly. Then add the spring to the piece in the middle, and we're going to stretch it to the long screw on the stepper motor. Now when you do your Pac-Man jumps, it should snap to the closed position. This will keep the stepper motor against the tape when we start printing. Next, we're assembling the wood pieces, and just like previous hack packs, there are cutouts and tabs that we can place rubber bands around. While this one is kind of cumbersome, eventually everything is lined up. The battery is usually held in with foam, and this is no exception. But this time we have cutouts we can place these stretchy band things through. I really like this because soon we're going to be using these for cable management, which I've wished for in previous videos. I would appreciate more in some zip ties, but this was a very pleasant surprise. Wiring took some effort, but there's a lot going on here. We'll start by plugging the stepper motors into the driver boards on each side. You'll know you have the right driver as the wires are not long enough to mix this up. Then we fish the driver board wires through the cable management bands under the battery and save these for later. We'll also feed the remaining wires through these bands, and the book has recommended sides to pull them through since it'll be easiest when plugging them into the Arduino. Just like in the Hackpack turret, we're plugging the power and ground together in a way that forms one big block. I recommend using some tape and wrapping this block because this was frustratingly loose on the turret. Like I said before with cable management, I'll use some of my own zip ties to tidy things up and provide strain relief. Stick the breadboard to the wood section, outlining it on top, and start plugging in your wires. They are all color-coded, and if a color is duplicated, then it's part of a bigger connector like the servo wires, so you should be able to get this first try. To load our tape, we'll first slide the sled with the pen all the way back, and it'll lock out of the way. Push back the tape spinning servo and load the provided purple tape. You can release the sled by pushing on the word push all the way to the right. Make sure your pen is in place, turn it on, click the joystick to start editing, and type in TK Makes, as a reminder to subscribe when you're all done. Click the joystick again to print, and again because we're sure we want to print. Now you can marvel at the wonder that is stepper motors, and wait for the inevitable Mark Rober video where he uses 1,000 of these to write his Christmas cards.